Hello, my name is Ivan Cheltsev. I'm a lecturer for the linear algebra part of this course. And this is an introductory lecture, which explain you on one particular example, why do we need linear algebra? So I decided to choose for this lecture very classical theorem of Charles, French mathematician, theorem about plane cubic curves. The theorem said that if you have two cubic curves in the plane such that the intersection consists of exactly 9 points, you fix 8 of them, and then you take any other cubic curves in the plane which pass through these 8 points. Then this cubic curve must contain the 9th remaining point of the intersection points. What is cubic curve? Cubic curve is a plane curve which is given by the polynomial equation of degree 3. In general, this polynomial equation looks like this. So it's basically, you see there's 10 coefficients, a1, a2, up to a10, there's some fixed real numbers. And this equation defines you some curve in the plane. Such curves are called cubic curves. They play a very important role in mathematics, in number theory, and in cryptography. After this course, you will be able to prove Charles theorem. And moreover, after this course, you will be able to check the theorem in every given example. Basically, if I give you example of two curves, very explicit, given just two equations, and I find for you 9 intersection points, and I ask you to check that the theorem holds for if you choose any 8 points out of this 9, you will be able to do this. Let's do this in one very explicit example. Let's fix two cubic curves in the plane. First, let's consider a picture. There's a real picture. Real picture means that I found equations of two cubic curves, a red one and a blue one. And I checked that these two curves intersect by 9 points. You can count 9 intersection points on this picture. And then basically I randomly picked up the yellow curve, cubic curve, which pass through 8 intersection points. And then you see that this curve, this yellow curve, actually passes through the 9th point as well. Okay, let's translate this into the algebra, into the language of equations. First, we fix the equation of the blue curve. The blue curve is given by this equation. This equation may look a bit ugly, but it's actually not ugly. You see all the coefficients here are integers. It was not easy to find such equation. You will see later why. And this is equation of the red curve. It also looks a little bit like too long to do any computation by hands. But fortunately, we have some computer algebra packages like Maple or MATLAB or Python, which actually can help you with all these computations. So, for example, I can find the intersection of these two curves. How? Okay, you can basically do it by hands with some tricks, or you can use, for example, Maple or Python. Okay, I used Python in this example, and I found these 8 very nice looking points. You see, very simple, and the 9th one. And the 9th one, you see, it's not so simple looking point. You may ask me why first 8 points look so simple and the 9th point doesn't look so simple. Okay, I don't want to answer the question now, but you can ask me any time after the lecture. Okay, so we fix this two example, and we want to check Charles theorem for the first 8 points. Basically, we want to prove that if we pick up any other cubic curve in the plane, which contains first 8 points, then this cubic curve must pass through this 9th point that looks a little bit ugly. Okay, how to do this? First, let me remind you that this third cubic curve is given by polynomial equation of degree 3. So it should look like this. So basically here, a1, a2, up to a10 are some fixed real numbers, which we don't know. But we assume for the proof of the theorem in this case, that this curve C contains 8 points. Yeah, intersection. So what does it mean? It basically means if you substitute coordinates of these 8 points into the equation of this curve, you must get 0. Okay, let's do this. You substitute and you get 8 equations for the coefficients of the curve. Basically, these are 8 conditions which guarantees that our curve contains all of these 8 points. Yeah. So for example, the first equation in this system of equations, it's exactly what happened if you substitute point 2, 3 into the polynomial equation on this slide here. And you see these equations are nice, they're linear. And basically what linear algebra does, linear algebra solves systems of linear equation. It helps you to solve and to understand how many solutions do you have. Yeah. Okay. So first of all, you may observe that we have 10 unknowns and 8 equations. This basically means intuitively that we should have solutions. And actually, linear algebra, one result in linear algebra, which you're going to learn in the next few weeks, tells you that you always have solution in this case. And actually, it tells you more that you have actually infinitely many solutions. For example, if you just randomly choose A8 to be this big number, and if you choose A9 to be this small number, then you can solve the system of now it's going to be 10 equations, yeah, because you have 8 equations on the previous slide, and you have 2 equations, A8 equal this big number and A9 equal this small number. You can solve it, for example, using, again, as I said, Python, and then you can check, in this case, there exists unique solution. And actually, there is some result in linear algebra which guarantees that in this case, you're going to have unique solutions once you fix these 2 coefficients. Yeah, and this is exactly the equation of the blue curve. Okay, now you can do the same with playing with other parameters. You can change A8, you can change A9, and you get equation of the red curve. Here, I just found equation of the red curve. So basically, it tells you, these 2 examples tells you that you should probably have infinitely many solutions, because you can change A8, A9 as you wish, and each time you're going to have unique solution, and this gives you a lot of curves in the plane. Okay, now we want to translate the system of equation in what is called matrix. If you never heard what matrix is, don't worry, you will learn a lot of things about matrices in this course. Let me just tell you that matrix is basically just a grid. So you take all these coefficients of the system of linear equations, which were 2 slides ago, and you just put them into the grid. Okay, let's do this. So you had 10 unknowns, 8 equations. These give you this matrix with 8 rows and 10 columns. So this matrix encodes all information about your system of linear equations. So if you basically have this matrix, you can recover the system of linear equation, and vice versa. If you have system of linear equations, you can recover this matrix. Okay, every matrix has a number which is called a rank. There's such number which you can define, and this is basically going to be one important part of this course. For every matrix, you can define its rank. There are many ways how you can do it, and you will learn that all of these different ways give you the same number. All of these different definitions of rank are equivalent. You don't know to know what this number is now. This is actually not the goal of this lecture. The goal of this lecture to show you the tools of the linear algebra which you can use to solve problems like this. So basically, there's some number related to this matrix, which is called rank. You can compute it, and you will learn tools how to compute the rank of the matrix. You can do it by hands. It's in this case, it's going to take quite a while because it's a big matrix. But you can, if you know the algorithm, you can do it. This is actually quite explicit. Or you can use any, as I said, computer algebra package, and it helps you to find the rank. So you compute the rank of this matrix, and it's 8. What does it tell you? It rank basically in formula. It's a number of non-redundant equations in your original system of linear equations. We had 8 equations, but who knows, maybe one of those equations is a sum of 2 others. Then, in this case, you don't need this equation, you can get rid of this. But this computation, the fact that the rank is 8, tells you that all your 8 equations are important. You cannot get rid of any of them. All of them are important. None of them is redundant. So this is what rank is. And then you use a very nice, beautiful result from linear algebra, which is called rank nullity theorem. You will learn soon what it is. Don't worry what it is, a beautiful result. But rank nullity theorem basically tells you if the rank is 8, in this case, and you have 10 unknowns, then all solutions of our system of equation can be obtained as a linear combinations of two solutions we already found. We already found two solutions, which is basically correspond to the red curve and the blue curve. And now, if you play around, if you take some of these two solutions, maybe with some coefficients, you take some number lambda and you multiply by the first solution, you take number mu, multiply by another solution, you add them, you get another solution. So rank nullity theorem tells you that in this way, you obtain all solutions of our system of equations. So basically, this means we solved the system of our 8 equations with 10 unknowns. This is the solution. Okay, just small remark, lambda and mu are Greek letters. In this course, we're going to use quite a lot of Greek letters, so you have to get used to this. They're very popular in mathematics. Okay, so we found everything. We solved the system of equations. We found basically what we just did. We found all curves, all cubic curves in the plane that pass through 8 points we fixed. Okay, now let's translate these solutions into the language of geometry. So this A1, A2, up to A10, the coefficients of the polynomial equation that define you some curves. Okay, what is the translation of this slide into geometry? It basically says the following. You take a polynomial which gives you the first curve, the blue curve, and then you take another polynomial called f2 in this case, that whose zeros give you the second curve, the red curve. And then what we just proved that every curve which passes through 8 points of the intersection, which we fixed, is given by the following equation. Some lambda times f1 plus mu times f2 equal to 0. So this is all possible curves which pass through 8 points. But now look, we also have a 9th point of an original intersection, so which I didn't put on the screen because this point is just too large. I mean, its coordinates are just too big. So if you substitute the coordinates of this 9th point, if this equation in a black box, what do you get? Okay, f1 of this point is 0 because this point is contained in the first curve. And also f2 of this point is also 0 because this point is contained in the red curve. So it means that this equation vanishes at this curve. We substitute this point in this polynomial equation, you get 0, 0 equal to 0. So this means that this point is contained in the curve C, which is exactly what we wanted to prove. Okay, this example shows you how to apply nice, good, important results, which you're going to learn this semester in this linear algebra part of this course, to prove some results in geometry. And basically, they show you that linear algebra is important, and its applications are everywhere in mathematics. So this is why you have to learn it and learn very well. Okay, good. Thank you. Let me stop this introductory lecture and see you in the next lecture.